Hello, and thank you for joining us today for our webcast. The future is now, choosing the right signage solutions with Peter Putnam, President of Rome Consulting. This webcast is sponsored and paid for by Panasonic Media Entertainment Company, including speaker fees. The opinions expressed in this webcast are those of the speaker. My name is Marian Sandberg, and I'm the Content Director for Live Design and the LDI Show, and I'll be your moderator today. Before we begin, just a few words about this webcast platform. First, you can customize your webcast console, moving windows around by dragging on the title bar, or resize them by clicking on the lower right corner of any window. And the toolbar at the bottom of your console allows you to open and close various widgets on your screen for instant use, such as the Twitter widget. If you experience any difficulties with audio or even the slides, please hit F key on your computer to refresh your screen. Finally, it's my pleasure to introduce today's presenter. Peter Putnam's company, Rome, provides training, marketing communications, and product development services. He publishes hdtvexpert.com and is a regular contributor to many industry trade publications. Peter is also a senior academy instructor for the International Communications Industries Association and was its Educator of the Year in 2008. We're very pleased to have Peter with us today. Peter, I'll hand it over to you now.
Thanks. And thank you, everybody, for joining in on this somewhat snowy day where I am, north of Philadelphia. Hopefully the weather's better where you are. We're going to spend the next hour talking about choosing the right display for digital signage. The market is wide open in terms of your choices. There are a lot of cool things that are going on. A lot of very fast occurring trends, too, that may shape your decision. Looking at the world of displays in 2018, we do have lots of choices to create large images for any purpose. But you can't just go out and buy one and put it to work. You have some questions that you need to answer first. Number one, the most obvious one, do I use a projection display or do I use direct view? Direct view, of course, being a large flat screen display. Do I use that for my application? Is there some kind of a dividing line between the two? Is it easy for me to say, let's say up to a certain screen size, I go direct view, and beyond that, I go projection? How bright an image do I need? And what about contrast? Both very, very important in digital signage applications. How will I get the signals into my display? There's a lot of things going on in that area. How will I access content for the display? And what's going on with 4K, which obviously is generating a lot of buzz in the AV industry. So we talked about that dividing line. Well, where is it? It's kind of hard to hit that. It's a moving target. It depends on the screen size and the geometry of the picture that you want, how much ambient light you have in the presentation space and how you choose to control it, your targeted resolution for your finished display, just how much detail you want on the screen, and of course the physical installation challenges, the viewing space it has to go into, and the costs of managing all of this. So in general, and this is not an absolute rule of thumb, so don't take it as that, single screen applications up to 84 inches diagonally can easily be handled with direct view displays. Some people will say 70 inches is the dividing line. Some will say 80 inches. Some will say 84. So let's say it's in that area, that general range. But once you start to get above 84 inches, your displays, your direct view displays, are very heavy. They're obviously very large, not easy to move around. And that's still pretty much the domain of projectors. There are some exceptions, obviously. It's still more cost-effective in getting to larger screen sizes because, as I said, the larger LCD screens are heavy. They're not all that easy to move. So these two are going to coexist. You know, we're not going to see one or the other pushed out of the market at the other's expense. Now, let's take a look at short throw and direct view. Short throw projection gives you seamless images scalable to any size with no mullions. And if you're using tiles and tile displays to get to a certain screen size, you are going to have mullions. And does that bother you? If it doesn't, great. If it does and you want a seamless image, projection at the moment is still the best way to go. It gives you scalable resolutions in both the horizontal and vertical axis, scalable aspect ratios, and no limitations on screen shapes, which is probably the biggest advantage of projection, is that you can make a screen shape any size you want, any geometry that you want. You can do 3D projection. By that, I don't mean necessarily projecting 3D images. I mean projecting onto multidimensional surfaces, such as a car, or a pyramid, or the Disney Enchanted Castle down in Orlando. For a large panoramic image, you have fewer display connections. If you're going to do panoramas with direct view, you have to have a display connection for every single segment in the link. And you have fast on-off power cycles if you're using laser phosphor projection, which is where the industry is headed. That's pretty much the future, and actually it's the present of projection. And relatively low maintenance because you're not replacing lamps and filters on a regular basis. For direct view, well, you have high brightness under normal ambient lighting in any environment, even outdoors. You can tile with thin mullions to create much larger displays. Again, if the mullions aren't that important to you, then you can get to a really big image by tiling multiple displays, multiple flat screen displays. It's a lot easier to enable a touchscreen overlay with a direct view monitor than it is with a projection system. You don't need any space. With projectors, you have to have some distance between the projector and the screen, even if you use ultra-short throw lenses. With a direct view, you don't have to deal with that. You can mount it right on a wall. There's no need to correct geometry or blend images when you're creating a larger display, but it can only really be a two-dimensional display using current flat screen technology. You also have the fast on-off cycles, and you have low maintenance. It's basically a backlight, an LCD shutter. You turn it on, you turn it off. So if one or the other could be said to have an advantage, you could say that for short throw, the advantage is the seamless images that are scalable to any size, that are free of mullions, scalable resolutions in the horizontal and vertical axis, scalable aspect ratios with no limitations on screen shapes, and being able to project onto three-dimensional surfaces. But the direct view, high brightness under normal ambient lighting, obviously if you're projecting on a surface and ambient light is hitting that surface, it's lowering the contrast and it's lowering the brightness. You can tile with thin mullions to create much larger displays. It's easier to enable touchscreen overlays in direct view. There's no space needed for projection, and you can mount them directly on walls. So let's start by taking a look at what's going on with laser phosphor projection. Okay, we hear about this. A lot of people say, is that actually a laser that's making the image? Well, no, it's not a laser. We're still using the same imaging devices to form the image, in this case, digital light processing, digital micromirror devices. But what we've done is we've gotten rid of the lamp. And now what we can do is use a laser, or more specifically an array of blue laser diodes, to give us all that illumination energy that we need. Going through a diffuser, you can't use direct laser light because it produces specular light. We then take that diffuse light and we run it through a color wheel with a yellow-green phosphor. And if you remember your color science from junior high school, when you combine blue and yellow, you get white light. So in a single chip DLP engine, that white light modulates a sequential color wheel. In a larger projector using 3 digital light processing chips, it modulates 3 separate DMDs. And the advantage here is the laser light engine is going to last a lot longer than a lamp. The industry figure is approximately 20,000 hours before you reach half brightness with a laser light engine. So on the left, you'll see a diagram of how this actually works. It's a little hard to get your head around this concept, but on the right, far right, we have the blue laser array, and there are multiple blue lasers to get up to the power that we need. Then we run it through the color wheel. The color wheel adds yellow into blue to give us white light. And then we have separate DMDs that are giving us red, green, and blue, depending on the sequencing of the, I'm sorry, this is a 3-chip, my mistake. This is a 3-chip, not a single chip, so we have 3 DMDs, and we have a blue laser engine sending light to a red, green, and blue DMD array. And those are adding up colors in real time to give you a full color image. So, chip. It's a little bit more complex because we still have the blue laser light engine that's working as it did before. And we retain the color wheel. And then we're taking a color filter. So we're taking red, green, and blue, and in some cases white light, sequentially pulsing that to the DMD. So for 1 split second, you're getting green light on the DMD. In another split second, you're getting red. Another split second, you get blue. And to get more brightness, then you get white. So when you add those all together, your eye doesn't see the transition between red, green, blue, and white. It just sees a full color image. It happens that quickly. So the laser light engine phosphor wheel, that doesn't change. What changes either a single chip with a color filter, spinning color filter wheel, or 3 DMDs. So some of the benefits of laser phosphor, you have a shorter startup time to image over a lamp. The colors remain stable over hours of operation. Even the best projection lamps over time, for the first 100 to 200 hours, you'll see a little bit drop off in brightness, and you'll see a shift in color away from, let's say, bluish to more yellowish. And with the laser phosphor projector, one of the cool things is you can place the projector in any orientation. Projection lamps are not necessarily happy operating, say, upside down, illuminating the floor. If you've been to an NBA game lately, they're doing a lot of projection mapping. Well, those projectors are mounted up in the ceiling, shooting straight down. But with laser phosphor, not a problem. Doesn't mind it. Your light engine is completely sealed, so you should not have any dust ingress over any period of time. And again, since it's basically like turning on and off a light, you're just turning on and off a light engine and modulating the light, you should have very low maintenance. This allows you to do 24/7 operation for digital signage. And the other thing about this, and do get asked this sometime, is the technology green? Well, the lasers certainly are. Keep in mind that projection lamps contain halides of metal. The most common one is halides of mercury, and mercury is a heavy metal, and it's a toxic metal. So this is really a greener solution than using lamps. Power consumption and light output. If we look at these particular Panasonic models, the RZ570 and RZ31, they're consuming about 13 to 14 watts of power per lumen, operating in normal operation. They can also be operated in dimmed mode, so a more economical operation. And of course, since lasers are solid-state light sources, it's pretty easy to dial them back for lower power operation if you don't need all that brightness. And the eco mode will stretch the life of the laser light array. Blue laser modules rated at about 20,000 hours to half brightness. That's not an absolute number, but it's an industry average. And half brightness would occur at about that. At that point, you'd be ready to replace the projector. Now, in eco mode, one of the cool things about it is your time to half brightness doubles because you're cutting a light output in half, so it's pretty logical. 12,000 lumens, let's say, in eco 1 over a 25,000 lumens for a PT RZ31K. So if you don't need 25,000 lumens and 12,000 is enough, well, then you can continue to run that for a lot longer. A basis of comparison, typical short arc mercury lamps would need to be replaced every 2,000 to 3,000 hours or 6 to 10 lamp changes over the same life of the laser array. Some short arc lamps require replacement even sooner. This has often been the case with high brightness projectors using xenon lamps, which can last 500 to 1,000 hours. So there is a clear advantage to moving to the laser light engine. You retain the luminous output, but you can double, triple, even quadruple the life of the projector. How about switching speeds and performance? Well, laser light engines can switch on and off at extremely high speeds. They have a very sharp on time and a very sharp off time, rise and fall time. Digital micrometer devices also switch on and off at very high speeds. That's how they produce continuous tone images. They use a technique called pulse width modulation. So when you combine those two, it allows you to, first of all, get really dynamic contrast from scene to scene. So when you're switching from a very bright scene to a very dark scene, it's almost an instantaneous switch. Power efficiency. Lasers can't be dimmed, but they can be switched using pulse width modulation. You can pulse a laser on and off very, very quickly, hundreds of times a second. Your eye will never see any flicker, but it does reduce power consumption. And actually, by pulsing it, so there's more off cycles than on cycles, you can dim the laser. Both cycles are fast enough to switch 60 hertz and 120 hertz video sources. And high frame rate video, not a lot is being discussed about it, but it's absolutely in the works, being able to show video at 100 or 120 hertz. And a system like this would be perfect for doing that. Now, in contrast, projection lamps are on continuously once they fire up, and they require a separate mechanical shutter mechanism to modulate the scene-to-scene contrast. It's not easy to do that with a lamp. So for energy conservation, a lamp may run at reduced power, but settings and choices are going to be limited. Laser phosphor engines have multiple eco settings. So you can set it to half. Maybe the manufacturer gives the ability to drop it to 1/4. But with a lamp, you may be able to reduce it by 20%, 30%. Once you start to reduce the brightness of a lamp below a certain point, it's not going to fire, and it's going to affect the color temperature of the lamp. So this diagram gives you a little better idea of how this all works. We're dynamically modulating contrast here, and we're using the pulse width modulation cycle. And by alternating the ratio of on to off cycles, if there's more ons than offs, the image is brighter. If there's more offs than ons, the image is darker. Contrast between scenes can be improved by as much as 20,000 to 1. It's a very simple switching process, and it's linked to scene brightness levels. So in the lower right, you'll see a mechanical dynamic iris responding to a change from a bright image to a dark image. And it's not really a sharp transition. It's a little bit of a sluggish transition down to dark, up to bright, and back to dark. Whereas with the laser, it's a very sharp knee. It's a very abrupt transition, very clear. So in this diagram, it gives you a better idea of just how fast that switches. In the middle is a dynamic iris system with a lamp, but on the right is a laser. So when you change from one gray value to another gray value, or from white to black, it is instantaneous. It happens extremely quickly. The other thing we can do is improve color rendering, which has always been a challenge for single-chip DLP projectors. 3-chip engines don't have any problems at all. They can easily do over 1 billion colors and 10-bit color. Single-chip engines have been limited by the color wheels. So if you have just pure color wheels, you can have better color saturation, but you may not be as bright. If you had a white segment, then you're reducing color saturation. And the challenge has always been, with these systems, reproducing warm colors, reds, oranges, and yellows. So one technique to get around this problem, pretty clever, add a second color wheel that has a magenta segment in it. Use this instead of a white segment when you want to improve color saturation. Well, how does that work? Well, this diagram shows you. On the left is a conventional wheel, and you can see it gives us a decent spread of color from yellow, red, blue, and green, but it's a little bit more skewed towards the green. So by adding the magenta, we can boost the red and reduce the yellow, which gives you a little bit better color rendering. So on the left, we're just going for brightness. So we have a clear color wheel and a multicolor segment, and we're just trying to get as bright an image as we can. But we have a little bit more yellow and a little bit more green in the image, not as much red, not as much blue. So by using that magenta color wheel, we can now increase the volume of the red, reduce the volume of the yellow. The blue remains about the same, and the green remains about the same. So it does give you improved color rendition. And this diagram may appear a little confusing, but I'll try to explain it as best I can. Yellow light passing through a magenta filter transforms to red as green light is blocked because it boosts the red output. Blue light passing through a magenta filter is unaltered. By adjusting the timing of the magenta color wheel segment, the spectral response in red to yellow frequencies is improved. So this approach works a lot better than the traditional single color wheel segment that's added to red, green, and blue and white to saturate colors. So not intuitively obvious, but the results are plain. This is a much better way to get improved color saturation with single chip DLP. So laser phosphor, which is the future, this is what everybody's heading to. Improved color rendering. We can get as much light now out of laser arrays as we can out of projection lamps. But another thing that's really cool is we can make the projector a lot smaller because a laser array doesn't have to take up so much room. So we've turned it into a high-powered lighting system that just happens to be able to show HD and Ultra HD images. So here's a product called the Space Player that can be used just as easily as a lighting system. It basically mounts in a track with its control system and power, horizontally, vertically projecting at any angle. Fast on-off cycles, very quiet operation, about 30 dB, which is pretty low. High brightness, good contrast under normal room lighting. And it supports either an HDMI input, an SD card input, or even still images over a wired and wireless local area network. So we've changed the whole concept of what a projector is considerably to the point where it's just another lighting instrument in some cases, but it's also a very high-powered real-time video display system. So what's going on with the direct view displays? Let's take a look over there. Well, it's no surprise that liquid crystal displays dominate the market. And this has been going on for some time, since the first 1080p LCD displays started to appear around 2004, 2005. It is a very mature technology. It is manufactured in Japan, Korea, China. It first appeared in the late 1990s for commercial displays, in the mid-2000s for consumer televisions. I am sure most of you who are listening today have at least one LCD TV in your house. Current benchmarks for LCD performance, it is possible to buy commercial displays as large as 98 inches diagonally. Resolutions to Ultra HD are common now. If you go into your newspaper for this past weekend, assuming some of you still get newspapers, and you look at the flyers, you will see loads and loads of ads for discounted Ultra HD LCD TVs. They have become commodities almost very quickly. Depending on the resolution of the LCD display, we can hit a brightness level of 700 candelas per meter squared. And they're available in obviously indoor, outdoor, and even touchscreen versions. Outdoor being weatherproofed. I mean, you can't necessarily soak these things, but you can leave them outside and they're resistant to water and dust ingress. Now, no secret, the trend towards larger, affordable LCD monitors has cut into the market for small room front projection systems, what we used to call the old hang and bangs years ago. Small conference rooms, meeting rooms, even fairly large classrooms now are switching over to LCD monitors. And in some cases, if the monitor isn't big enough for the room, they will put multiple monitors around the room. I've seen this used at several major universities in the Midwest. The consideration here, of course, is that you're in a classroom, it's a high ambient light environment by design. You're not really going to dim the classroom lighting. You want to keep the lights up. So that is one of the things that's driving adoption of LCDs. And of course, you can tile them to create higher resolution images. So you could take 55-inch 1080p monitors, take 4 of those with thin mullions, put them together, and what do you have? You have a 110-inch display with effectively 3840 by 2160, or what we call Ultra HD resolution. Now, the LCD panels are being fabbed and cut on ever larger assembly lines. There are plants being built, mostly in China now, but they're built in what's called generations. And each generation can cut larger pieces of what are known as mother glass. That is the large master glass that comes off the line. And then that is cut into smaller pieces. So you can do two things here. You can either cut much smaller pieces of glass at lower costs, or you can make larger pieces of glass at lower cost, not as many. And both of those are what are driving the market. So the manufacturing is taking place in Japan, Korea, Taiwan, and China. Panel prices have dropped considerably over the past 5 years. Again, just look at the prices for televisions. Televisions are the biggest market for LCD panels. And what happens with LCD panel pricing is largely tied to what's happening with consumer LCD television pricing. There have been numerous enhancements to backlighting technology and color imaging. When these panels first came out, we used what was called a cold cathode fluorescent light. That's pretty much a dinosaur now. TVs use light-emitting diodes as backlights, either on the edge to make them super thin, or directly behind the LCD panel, what's called a direct illumination. And then we have some other technologies like quantum dots coming into the market that can produce really intense, purely saturated reds and greens combined with blue LEDs to create high dynamic range images. And there's a shift happening now to Ultra HD resolution glass, and this is evidenced again by today's consumer television market. Look at those flyers. I have right in front of me a flyer for a chain in the New York area, PC Richard, and literally every TV they're advertising up to 75 inches on every page is a 4K TV. So what this is doing is it's leading the manufacturers to start ramping back on full HD or 1080p glass production and ramping up Ultra HD glass production because the costs, the finished costs to make the panels have basically reached parity. It's the same. So if you are a manufacturer, you say, I'm just going to start making 4K glass. And I'm not going to make as much 1080p glass or even make it at all. So we've reached price parity, and the expansion hand in hand with this, we're seeing an expansion to larger glass sizes. So whereas years ago we might have thought, wow, a 42-inch display is a big display, that's not such a big deal anymore because it's pretty easy to get to 65 inches, 70 inches, 75 inches, 84 inches, and now even 98 inches, although the 98-inch product is still largely a commercial product. And by going to Ultra HD resolution, we create a challenge for ourselves because we're packing more pixels into a given frame at the same refresh rate, and we're using deeper colors, so we have to have faster display interfaces. And both DisplayPort and HDMI have responded to this, and I'll get into that towards the end of the seminar to show you exactly what's changed. So the previous big seller was 42 inches. We joke about it, but it was exciting to get that 42-inch TV. But now the 42-inch TVs are winding up in the kid's bedroom or their, a spare room or something like that. And if you were out shopping at BJ's or Costco or one of those places during the holidays, you probably saw people running out of the stores with 55, 60s, and 65-inch screens. Well, there's a reason for that. The sweet spot now in terms of sales and in terms of panel production is in that 50 to 55-inch range, and that is becoming the sweet spot. HD resolution is most common at 43 to 84 inches. You can still get it in larger panels, but now we're starting to see, because of this decision at the plant level to manufacture Ultra HD, larger panels coming out with Ultra HD resolution, 84 and 98 inches. And for these panels, for commercial displays, the landscape orientations are standard, but some models, for example, the 84-inch that you see here, can actually function in portrait mode. And that's important, too, for digital signage applications where you don't have a lot of space, or you want to model something or show something that is vertical, maybe clothing, machinery, lighting. So the fact that you can spin these and turn them 90 degrees, that's a big deal. We're not going to get into a lot of technical detail here, but when we talk about LCDs, there's basically two different ways that the panels are made, and it has to do with how the little liquid crystals twist around. One is vertically aligned, VA panel, which is very, very common. That's very common for consumer televisions. And the other is in-plane switching and variations of it, which is advanced IPS, super IPS, ultra IPS, also IPS alpha. And this is preferred for large LCD displays. If you look at any color critical monitors that are used for color grading, for matching paints, paint colors, ink colors, dye colors, commercial monitors, generally people prefer IPS. IPS has a much wider viewing angle than VA, but more importantly, you don't see a color shift. It's hard to avoid a color shift with vertically aligned glass. You don't see that with in-plane switching glass. So for a professional monitor, it really is the way to go. It's the better of the two technologies. For now, things can change. There's constantly improvements being made to both technologies, but coming back from CES and seeing some of the latest IPS displays, I was very, very impressed with both the off-axis viewing and the color saturation. Well, so IPS, in a nutshell, the liquid crystals, and there are liquid crystal compounds. They come from actually a paste that's applied when the panel is made. They're either oriented horizontally or rotate on axis to pass or shutter light through the panel. So I mentioned Super IPS, IPS Alpha, and Ultra IPS. These are enhancements. It still uses the same alignment layer, but there's constantly tinkering with the process and tinkering with the panels to improve off-axis viewing and color saturation. And they do have better performance. The VA glass is getting closer. It's getting a lot closer. But for the vast majority of commercial displays that you see, the IPS still has the edge. And they are used in professional and reference grading monitors, as we mentioned earlier. Now, some performance benchmarks to get into. It depends on the pixel density. It depends on if it's a 1080p panel or an Ultra HD panel. But your brightness can range from 300 to 400 candela per square meter, or nits, as some people call it. Some panels can actually hit 700 nits. Those tend to be full HD panels and not Ultra HD panels. Contrast, 1200 to 1 to 1400 to 1. This is real world. We're not going to say it's 1,000,000 to 1 or some of these crazy numbers that involve jiggering the ambient light. But 1200 to 1 to 1400 to 1, which is more than adequate for public viewing. In terms of power consumption, varies from size to size, but if you look at the spec sheets, you'll see it averages about 5 to 7 watts per nit across all sizes. Those of you who remember the days of plasma, how much power plasma displays consumed, I had a 42-inch 1080p plasma that was 375 watts was what it was rated at. A 42-inch 1080p LCD panel might use 160, 150 watts. The average power consumption is about 15 to 30% lower than the peak, and that's actually measured using the IEC 6287 measurement method. So this has been quantified in the lab. Time to panel half brightness depends on the LEDs that are used. 50,000 hours at 77 degrees Fahrenheit sustain. This has also been tested. Not every panel will hit that number, but it's a good number to shoot for. LCD panels largely use white LED backlights, and they have color filters between the backlights and the panel to give you the red, green, and blue that you need. And they can all approximate what's known as the ITU recommendation BT709 color space. That's the color space that we currently use for high definition television. I mentioned earlier using smaller LCD displays to build large tiled video walls. Now, how do we do it? Well, if you have 4K displays, they provide 4 times the image resolution of 2K in equivalent screen sizes. It's 2 times horizontal, 2 times vertical. You could use a single 4K display and you don't have any mullions, but a 4K panel tends to be heavier and larger, and commercial models currently start at 84 inches and go up from there. Now, we may eventually see some smaller 4K displays, such as 55 inches and 65 inches. But for the time being, as we're easing into this market, 84 and up is what we're looking at. That could all change next week at ISE, could change it at Infocom. So you want to look sharp for that sort of trend and see, are we going to see more high-resolution Ultra HD displays in smaller panel sizes? The weight and installation issues are not insubstantial with a large screen. I remember years ago, somebody trying to show a very large 4K display in a suite in one of the hotels in Vegas, and they couldn't figure out how to get it in and out of the elevator. They hadn't thought that part out. So one workaround is, could we use 4 smaller tiled full HD displays to get to the same resolution? Well, we could. If we have 4 43-inch displays, that buys us an 86-inch screen, and our additive total resolution is 4K. So it would be 3840 by 2160. Or we could take 4 55-inch displays to get to 110 inches with 4K total resolution. So the design consideration is, do you go larger with shorter viewing distances? That's why you'd want to use 4K. Remember, the recommendation with a full HD display is to stand about 7 times the screen height for, let's say, standard video, so 3.5 times the screen height to go to 4K. But if you go to an 8K even display, and we're starting to see those come to market, you could be as close as 1.5 feet from the display before you'd see any sort of pixel structure. Not that we're ready to do 8K yet, but it is in the works, and we're going to see 8K displays in the next few years come to market. And then how do you connect everything? So do you use HD-base-T, HDMI, fiber optics, next-gen HD-SDI, copper fiber? All of these things need to be taken into consideration if you're going to build a large tiled video wall. So on the left, you see a 4K display. What we did was we took 4 43-inch monitors, and we came up with an 86-inch diagonal image. But it's comparatively inexpensive to put this together. The monitors are not heavy. It is a 4-piece installation. It does require outboard image processing, so we have to segment the image into the 4 quadrants unless one of the monitors will do it for us automatically. Otherwise, we have 4 DisplayPort or 4 HDMI connections to get into this monitor. But it got us to 4K. Now on the right, we might say, well, why don't we just put up an 84-inch single 4K monitor? Okay, we give up 2 inches, but we're not going to quibble over that. It does give you a mullion-free image. That may be important, but it is heavy, and it is going to cost you more money. The panel is more expensive. But on the other hand, it's a 1-piece installation, assuming you've figured out how to get it into the presentation space where you want to be. And depending on the signal source, it may require some additional outboard image processing. So I don't necessarily have an answer for you one way or the other. I'm just saying there's 2 ways to approach this problem. On the left, 4 monitors, small monitors, lightweight, inexpensive, gets you to 86 inches, got more cabling to do, and you need some outboard image processing to drive it. On the right, single panel, heavier, more expensive. It is one piece. It may require outboard image processing. So I mentioned earlier that 55-inch is becoming a very, very popular production size at LCD fabs in Asia. And it will become a very popular size over here too. And it makes a great tile size. So we can take 55-inch monitors and we can put these together in a wall, which is a 3x4 wall, and the effective resolution we wind up with is 7680 by 3240. Well, 7680 by 3420 is 8K. So this is almost 8K resolution just using 55-inch monitors. We want to go with thin mullions, as are offered by these particular monitors, to reduce the seams. If you're standing back far enough, they're not really that annoying. Some of us just like to have seamless images. And in terms of benchmarks, these are all IPS panels. They're full HD panels, 1920 by 1080, which are not terribly expensive. The brightness is rated at 500 to 700 candles per square meter, which is a very, very bright image. Contrast rated at 1200 to 1. Sounds great, right? Well, again, it does require special video processing because we are remapping across 12 different monitors. So it's very important to make sure the content that you use is the highest resolution possible because you're going to be magnifying it several times by the time you segment it and display it on a tile display like this. And there's 4K. So what's going on with 4K? You know, it's very easy to buy 4K TV. What's going on in the market? Well, it is available in projectors. 3840, 2160 is Ultra HD video. 4096 by 2160 is true 4K. Both of these are available. 4K 4096 is really more of a professional format. Ultra HD is more of a consumer format. So what we have here is a really interesting solution to getting to 4K. This is the PT RQ32K. It's a 4K plus projector. Well, we say plus because it's 5120 by 3200 pixels using something called quad drive. 4 times the resolution of 1080p. It does require faster clock and data rates because you're putting a lot more pixels, 4 times the number of pixels as you're doing with full HD at the same refresh rate. Enhancements that will follow for projection, high dynamic range, a wider color space, which, by the way, goes hand in hand with HDR. It's the BT2020 space. It is considerably larger than the 709 space that we're used to now. And that's because we have really saturated colors that have higher luminous values and higher frame rates. I mentioned that earlier, too. We have gamers, virtual reality, people that want 100, 120 hertz frame rates. Well, laser phosphor is well positioned for all these features, as we saw earlier. It can switch fast enough to handle 120 hertz. It can do high dynamic range. It can do a wider color space. Some definitions you may find useful here, and these are actually to scale. Ultra HD has the resolution of 4 times the resolution of 2K panels. So I can fit 4 of the full HD screens in the upper left into the screen on the right. With a blanking interval, the additional clock and blanking information, a typical 4K frame is 4400 by 2250 pixels. What we see as Ultra HD is 3840 by 2160, but it's the same aspect ratio as Full HD. It's 16 by 9 or 1.77 to 1. Cinema 4K, as I mentioned earlier, professional 4K, uses the same vertical resolution, but has 4096 horizontal pixels. So it's a little bit wider. And while the vertical resolution remains the same, we've changed the aspect ratio now to 1.89 to 1. HDR, very exciting development. It's easy to see. People get it, and it's coming. And it's going to become a pretty standard feature in short order. So on the left, one of my favorite places in the world, in Italy, that's the town of La Spezia, which, some trivia for you, that's where pesto was invented. A 4K image captured with standard dynamic range on the left. We can see a little detail in the clouds. Can't really see much in the foreground. But on the right side, we can see more detail in the foreground. The color saturation is improved, and we can see a lot more detail in the clouds. So HDR provides higher contrast and better shadow detail, but To do it, you have to have 10-bit and 12-bit color rendering. We've been using 8-bit color for several decades now. Now we need additional bits to render these images correctly. And here's that new color space, the ITU recommendation BT2020. If you look to the diagram on the right, you'll see the HD space we use, the 709 space, is in the yellow triangle. Well, the 2020 space is the black triangle. And if you go all the way to the very top, that locus at the very top in the green, probably the only thing that can actually hit that is a laser by itself. So we're not going to get all of this with these new color spaces in our new imaging system. So we're going to get a lot more than 709. And if we're using 10-bit color, we've got 1,073,741,824 colors, as opposed to the 16.7 million colors you get with 8-bit. That's closer to human color sensitivity. High frame rates, again, very exciting thing. Those of you who have been to NAB may have seen NHK showing this. They've been broadcasting in 8K since 2012. They've covered all the Olympics in 8K. And now they're shooting at 120 hertz, so you don't see any blur at all. A new SMPTE standard has been developed for this, and it will support 48, 50, 59, 9, 4, 60, 96, 100, and even 120 hertz at 4K and even 8K. And just for fun, an 8K image at 120 hertz is 192 gigabits a second if you're using RGB or 444 color. That's a ton of data to move through an interface. So our laser phosphor projectors are ready for this. They can support this. They can do over 500 hertz switching. And this is important if we're going to see these things for virtual reality, any immersive environment, and more increasingly, live sports and entertainment coverage. We can go beyond 4K. How about 5K? 7 times the resolution of 2K. So it's 5120 by 2880, same aspect ratio, 1.77 to 1. Another way to get to Ultra HD. You can use a projector with native 4K imaging chips. It's pretty costly. Right now, those are high brightness, theater quality projectors, and they're not inexpensive. Another way to get to it is to use lower resolution imaging chips, 2560 by 1600. And what you do is you shift the pixels and modulate each quadrant of the screen at high speed. Remember, this happens very quickly, much faster than your eye can see the transition. So your 4K content is upscaled to 5120 by 2700 pixels, and Ultra HD is upscaled to 5120 by 2880 pixels. And the final image appears as a full resolution 4K image with no flicker. You don't see the image shifting. This technique's been used for quite a while. There's a lot of different ways to get to it, but this uses 2560 by 1600 pixel digital micromirror devices. And we shift them very, very quickly with each frame of video, and the net result is you have a little bit more than 4K resolution. It makes for a more affordable way to get to 4K front projection. So you're asking, well, how does that work? Well, on the top you see conventional pixel quadrupling technology. Okay, you take a original pixel, say 2.5K, and what you do is by shifting the mirror slightly, you modulate red, green, blue, and yellow, and you create a 4K image. And then a real motion processor is used to take the 60 frames per second signal coming in and upscale that to 5120 by 2880 as the signal is being modulated. As we're tilting the mirrors to modulate each segment of the 5K image. And the net result is we wind up with a 4K plus image. So we have 4 different frames, full color frames, and it's 4K. A little bit more than 4K or around 4K. So a very effective way to get to 5K resolution. Now, direct view displays in 4K, what's going on with them? All large 4K LCD displays are Ultra HD. By that I mean anything over 84 inches. And we've seen displays as big as 120 inches. Prototypes, not ready for the market yet, but they're in the works. Glass cuts, when we cut apart those big, big sheets of glass, just like we cut up brownies from a baking sheet, we start at 55 inches, we go all the way to 98 inches. That's the commercial limit right now. Panels using IPS alpha and IPS variant technology. The backlights are white LEDs. Color comes from color filters, precision color filters that actually have phosphor compounds embedded in them. Color gamut coverage is BT709 at the present. We're not doing HDR yet. It'll come, but give it some time. And for a 4K monitor, these are reasonable specifications. 400 to 450 $10 per square meter of brightness, and 1400 to 1 contrast. Now, these monitors can do some cool things. They can show you a single 4K image, or they can show you 4 full HD images. You have 4 HDMI 1.3 or 1.4 connections, so each one of those is good to 10.2 gigabits a second. So we can show that full UHD image mapped outboard, or we can show 4 tiled images simultaneously. So this is one easy way to do a multi-segment image for something like command and control or a mother monitoring application. And these really aren't the same old monitors that we used to see in the past. They can work inside, they can work outside, they can work with touchscreens. They come in full HD and Ultra HD resolutions, and at some point in the future they'll come with 8K resolutions. Can't say exactly when that's going to happen, but I've seen plenty of them on my trips to Asia. LCD monitors can make up tiles in larger displays with additive resolution, real easy way to get to high resolution. They operate with single images or as multi-viewers in Ultra HD mode, and they can signal mobile devices for custom content download. So that's in itself pretty interesting. Your LCD monitor can actually talk to your mobile phone or your tablet, and it can signal to have content downloaded to that device based on something you saw displayed on the monitor. Connectivity. It's great to have all these extra pixels, be able to do high frame rates, everything else, but we have to have a connection that's fast enough to get into these displays. So we have a bunch of options here. We can use uncompressed display connections, such as HD SDI. We can do HDMI over category cable, which is HD base T. That's essentially what it is. We can go over an IT network with format conversion, so we can use MPEG or JPEG compression. We can use USB memory sticks and load it right into the display and have the display play it back. Or multiple 3G SDI inputs, so 4 times for 12G. So if you're going to do 4K, you need a 12G connection. We're not really at single 12G connections yet. So what most people are doing is using multiple 3G. That's full HD, 3 gigabits a second, using 4 of those to get to 12G. HDMI, first introduced in 2002. Hard to believe it's been around for 16 years. Has a maximum clock speed of 330 megahertz. Also carries transition minimized differential signaling. Display and audio. It's consumer-friendly, plug and play. Not necessarily a great interface for commercial, but it's the most popular display interface in the world. Everybody uses it, so you have to support it. Version 1.3 and 1.4 is a maximum data rate of 10.2 gigabits a second, including all the overhead. There's additional 2 bits of overhead for every 8 bits of signal that goes through this connection. But we're not standing put here. Right now, it can do the HDMI version 1.3 and 1.4 can do Cinema 4K or Ultra HD, but it can't go over 10.2 gigabits a second. It can do 8 channels of linear pulse code modulation. It has an Ethernet return channel, an audio return channel, and it supports 3D video. Well, a new version was announced in 2013, not 2003 as you see there, with a maximum pixel clock of 600 megahertz. Well, that allows us to do 4K with 8-bit color at 60 hertz, RGB color, 444 for those in the broadcast world, 32 channels of 1.536 megahertz audio, and version A, B, and G support high dynamic range metadata, CT861 3 metadata, and compatible with USB 3.0, 3.1 Type-C mode. That's the tiny little USB connector you're starting to see pop up on computers. And it's been a while. We're starting to see it widely adopted in Pro AV. It took about 3 or 4 years for people to pick up on this. But 18 gigs is 8 gigs faster than 10.2, roughly, and we need it if we're going to start doing 4K. But we're not stopping there. So HDMI 2.1 was announced last year and then re-announced this year, because last year it was more vaporware. And now they're pushing the speed to 48 gigabits a second. Well, that's clearly fiber optic territory. By using 4 lanes to carry the display signal with an embedded clock as opposed to 3, doubling the physical layer speed from 6 to 12 gigabits per lane using a different form of coding to reduce the overhead, but it means you have to have new cables. And strangely enough, there's still no optical interface specification for version 2.1 yet. It does support USB Type-C alternate mode, and it does support something called display stream compression. It can actually be compressed. Well, what about DisplayPort? It's been around. First version was 2006. Current version is 2.1, introduced in 2009. It is faster than HDMI 2.0. Its maximum data rate is 21.6 gigabits a second. It was very popular for a while with Apple. HP, Lenovo, and other companies are now using it, although they're kind of hedging their bets by supporting both DisplayPort and HDMI. And they have shown some enhancements to it, version 1.3 in 2014 and version 1.4 in 2016. Both those versions increased the data rate to 32 gigabits a second by having 8.1 gigs per lane. Well, that's fast enough to do an Ultra HD or Cinema 4K image at 60 hertz with 16-bit RGB color. That's a ton of data. Or drive two 4K displays simultaneously. You can also drive a single 5120 by 2880 60 hertz display. Apple has a very fine resolution monitor that uses that particular display. It supports display stream compression, version 1.1, compatible with USB Type-C, and supports HDR, version 1.4, increased support for HDR and other color modes than RGB or 444. So it supports 420 and 422. Also supports CTA HDR metadata by necessity. And it adds forward error correction, because the last thing we've compressed in the display chain is the display interface. We've never done that until now. Well, why not? We can achieve some efficiencies there, especially if we're going to be showing 8K at some point. And also supports 32 channels of audio and the same data rate as HDMI 2.0. And it'll actually do 8K 60 or 4K 120 with deep color. That's how fast this interface is. HD-based-T, I'm sure most of you are familiar with it. I won't go into a lot of detail here. Version 2.0 added network switching control point capabilities over version 1, and it supports USB 2.0. And you can make a very small switch and less costly switch using HD-based-T. It doubles the throughput in an upstream sublink and allows for local retransmission. It's developed by Valence Semiconductor, converts HDMI to packets, and mixes in Ethernet, infrared, RS-232, audio, and a bunch of other things. Still has a maximum transmission distance of about 100 feet or 328 meters. It can now also supply power over Ethernet to remotely connected devices. Our playback options, we've talked about interfacing, but if we want to do it locally, all of these work: flash drives, SDHC cards. We can daisy chain our displays for media playback if we want to. So one display can be playing the content, and then we can feed that to additional displays down the chain. And we can use multiple content playback devices just in case we have dropout. So we can actually be feeding it from a remote source, but have the same thing loaded on a flash drive or an SD card at the display in case for some reason the network drops out on us. This is what I mentioned earlier, the link race system. LCD monitors and lighting fixtures can modulate signals. And as I said earlier, you can turn the backlights on these things on and off really quickly, but you don't see the flicker. Well, your phone would. So you can actually use the light in a display to modulate very quickly and send a burst of information to your phone. And then your phone uses a special app and a camera to pick up on that pulse light sequence. And that pulse light sequence is basically a barcode. It's some sort of a QF code or a QR code. And then what happens is you click on that, and then content relevant to what you're seeing on the display comes over a Wi-Fi or an LTE network directly to your mobile device. Pretty cool. Check it out next time you're at one of the shows. Again, you will not see the display flickering at all, but your phone absolutely picks up on this. It's just a really inventive way to use the illumination coming from a display to connect to people. And just a few words about networked AV before we wrap up. This is all the rage now. You're going to see this at ISE next week. Everybody is, after many companies poo-pooed this, now all of a sudden they jumped on the bandwagon and everybody's saying this is the way to go. And it is. The broadcast industry, communications, telecommunications, everybody else is using everything over a network. And we're going to join them. It's just taking a little while. So we're going to move away from worrying about is it HDMI, DVI, or SDI, or whatever it is, and converting that. And we're just going to convert a signal using a codec. Take that codec, modulate the signal, and send it over a network with IP headers. So when you go to the shows, you heard people talk about H.264 MPEG-4. It's probably the most common codec in our industry. It has high latency, so you can't use it for real-time digital signage or image magnification. It's for remote delivery where latency is not an issue, but it's extremely efficient, very bandwidth efficient. H.265, not quite ready for our market yet, although you see a couple companies are showing it. It's a much more software-intensive codec, but it's been demonstrated to be 50% more efficient than H.264, and it will be the codec of preference for 4K. JPEG 2000, which has very low latency, high bit rates. We're already using it for digital cinema and motion JPEG, a variation on that, also a lower latency codec. Both these JPEG 2000 codecs are extremely low latency, so you can use them for real time. But there's no forward error correction built into them, and if you drop data, you lose the data. So in a more critical application, you might want to use an MPEG-based codec. But if you're going to do image magnification or live event simultaneously to multiple screens, JPEG is a perfectly acceptable way to go. All the manufacturers are going to support this by the end of the decade. They have to. This is clearly the future of where AV is going. And in the future, this is what a matrix switcher will look like. It won't be this big bulky thing in a rack. It's going to be, this is a 48-port switcher, if I'm not mistaken, rated at 10 gigabits a second. So that gives you one input connection and 47 output connections, and it's all done using software switching. H.264, very efficient lossless codec. I'm not going to spend a lot of time on this because we're getting close to the end of the seminar. It's 50% more efficient than MPEG-2. It does introduce latency, not suitable for live events. Really best for nonlinear content distribution over networks. You can take 1080p and pack it down to 5 to 10 megabits per stream using this. 265 was introduced a few years ago, cuts the bit rate in half, but it's a much more computational intensive. It requires a lot of computing power to make this work. Totally different method to digitize and compress video. Does introduce latency. Best used again for nonlinear content distribution over networks. But you can pack 4K content down to 15 to 30 megabits per second. It's been demonstrated more than once at NAB and other shows that you can do this. And it'll go over a network. JPEG 2000 provides high quality video compression, about 4:1 to 6:1. You don't really want to go much more above that because you'll start to see artifacts. It does require a very high bit rate, even though it's low latency. That's the trade-off. All the frames are key frames. There's no intermediate frames like you have with 264. There's no support for audio. You need a separate codec to make this work. And you can travel these through a network with IP headers. And finally, motion JPEG. Each video frame or interlaced field of a digital video sequence is compressed separately. It's widely used by digital cameras, IP cameras, and webcams, supported by nonlinear video editing systems. It used to be supported by QuickTime, Safari, and Chrome. It appears that only Chrome right now still supports it. Everybody else has drop support for this, so I will update that slide. Maximum compression is about 4:1. I've seen systems doing 20:1. It's softer. It's efficient, but you can tell there's a degradation in the picture. It's not as crisp. And this can also travel with IP headers. And on a network, basic Wi-Fi connectivity allows you to stream your presentation directly to the display. It can either be built in or use external electronics. Multiple participants in a meeting can share their files or desktops. Miracast is a popular choice. There's a number of different products on the market that allow you to do this. The challenge for all these guys is being able to stream 1080p 60 video. That's not easy to do, especially from multiple devices. So to summarize, because we are right at the top of the hour, projection and direct view displays coexist very nicely, despite what you may have heard. Direct view LCD is good for simple installs, no geometry correction. High brightness, good contrast under high ambient light. They could be tiled to create additive resolution displays. They're easy to integrate with a touchscreen surface. They can also create interactive communication. Projection is good for really large screens, seamless panoramas, nonlinear surfaces, curved surfaces, displaying images on unusual surfaces like water or glass, and having really high resolution in a single image. So you just need to know what you want before you buy, what you need before you buy. Do your homework, ask your questions. Don't There's no such thing as stupid questions when it comes to this. You may not get the best answers, but the more questions you buy, the more confident you'll be with your particular choice of display. So projection, direct view, there's a little bit of a dividing line, but if you take all these factors into consideration and how to connect all of it, you'll make the right decision. I have confidence in you. And that concludes my presentation.
Thanks so much, Peter. I do want to just take one or two questions, even though we're just at the top of the hour, if that's okay. There were quite a few questions that came in about OLED and what your opinion is about that technology, and also how it plays into different markets and where it's going.
Okay, well, OLEDs, organic light emitting diodes, are like LEDs. There's no question that we're seeing LEDs pop up in everything. The LEDs you see in outdoor stadiums and things like that, that's inorganic LEDs, just like the same LED that lights up on your phone when you get a message. Organic LED is a different structure. It can be made on plastic. It can be made flexible. There's really only a handful of companies manufacturing this technology. There's a cost premium associated with using it, but I have seen demonstrations of it in digital signage. So yes, it has tons of potential. It's not going to be as bright as an LCD presently. I can't say for sure where that technology is going to go in terms of brightness improvements. I have visited factories in Asia where these are made, talked to the engineers. So right now you're seeing it break out for televisions. That's what they're hoping is they can get a high uptick rate, acceptance rate in the consumer television market, which of course will drive further developments in OLEDs, reduce the cost of manufacturing these things. But yeah, you could wrap an OLED around a pipe. You can wrap it into a U shape and stand in the middle of it. That's a very immersive virtual reality solution. I've seen demonstrations of it used for car dashboards, which are very cool. Those were shown at CES, where you customize your own dashboard. And you can even roll it up. There was a roll-up 65-inch shown at CES. So you'll see some of it trickling into the market. Right now, that's going to be a very small portion of the market compared to LCD, because again, the LCD technology is mature. It's manufactured with very high yields. It's very affordable, and there's a lot of things that you can do with it. At some point, OLED may displace some of that. I can't really tell you how fast that's going to happen. I do like what I see, just that it's a bit of ways in the future.
We had a question specific to 3 to 5 mil LED video walls, and I'm not sure in which application or market, but the question comes, what are your thoughts specifically about 3 to 5 millimeter LED video walls? Okay,
kind of off topic here, but I think what they're referring to is the pitch of the LEDs, not the mullions. I'm not just going to go out there and say it's 3 to 5 millimeter.
Millimeter pitch, I would agree, yes.
Okay, yeah. Well, we're already seeing pitches well below that. I mean, people who have been going to the shows have seen pitches down below 1 millimeter, because the big thing now is micro LEDs. That's what everybody's talking about. But there's a tremendous cost associated with micro LEDs at the present. 3 to 5 millimeter for outdoor is fine. 5 millimeter is a little bit coarse for indoor viewing, unless you're standing some distance away. So typically 4, 5, 6 millimeter walls are used outside where people are viewing at some distance. 3 millimeter is okay, it's acceptable. You can get a little bit closer to that. But I would think indoor ultimately is going to go down below 2. And there are a lot of solutions out there that are doing 1.8, 1.5, even 1.2 millimeter walls. And those can do native 4K resolution. Just to give you some perspective, a dot pitch of 1.2 millimeter, that's the same pixel pitch that you would have had you bought a 50-inch 768p plasma monitor back in 1998 and paid an astronomical amount of money for it. So think about that. That's the same pitch from a monitor from 20 years ago, a 50-inch monitor, and that's now present in a wall. So yes, there's no hiding the fact that LEDs are making tremendous inroads into all aspects of the display market. Are they the right solution for everything? Not necessarily, but they're certainly good for, say, outdoor large venues, high brightness, where you have no control over lighting. And indoors, they work really well. They're extremely bright, but you have to be careful about which pitch you select for it, because you don't really want to have a really coarse image. People don't like the look of that.
Well, thanks for all that really great information, Peter. We don't want to keep everyone too much longer since we're over time. But before we sign off, I'd, of course, like to thank you so much, Peter Putnam, for this great presentation. And, of course, to our sponsor, Panasonic Media Entertainment Company. You can visit them at live.panasonic.com locally in the United States, or of course at panasonic.com everywhere. And please feel free to visit livedesignonline.com for more information about all of our webcasts, including several more coming up from Panasonic. And the on-demand version of this webcast will be available on the Live Design website within the next 48 hours. Everyone who has registered will receive a link for the on-demand version as well. Thank you so much for attending, and have a wonderful remainder of your day.